All right, so today will just be a nice, breezy, easy introduction to the second to last topic in this course, which is dynamic programming. Basically, don't let the name fool you. Dynamic, literally, if you look into the history of it, was just a fancy marketing term. I think it was this guy that was doing was looking for research dollars from the Department of Defense, and so he came up with this research proposal, which basically was dynamic programming, and he needed a fancy term to sell the proposal, and so he just called it dynamic programming instead of just regular programming or something. Look it up. I'm sure that story is on Wikipedia, but the basic idea, when it gets down to it, is you take a divide and conquer approach to solving a problem, which we've done before, merge sort, binary search, stuff like that. And then you develop a recursive solution to it, but then you realize that recursion is kind of bad, right? Because one, it risks deep recursion and stack overflows. Two, there's an overhead associated with recursion that you want to eliminate. And also, a lot of problems that you can do recursively end up doing a massive amount of overwork. For example, the classic Fibonacci sequence. If you look at that from a recursive point of view and draw out this big giant tree, then you'll realize that to compute the Fibonacci of 10, you end up computing the Fibonacci of 2 an exponential number of times, and that's not acceptable. So what you do, the idea of dynamic programming is to come up with a way of eliminating that redundancy using memoization, which we'll review here in a second, caching basically, so that you don't recompute Fibonacci of 2 over and over and over again. Instead, you store it off in some data structure. Dynamic programming simply takes the last final step in that process and says, all right, we don't need to have a recursion at all if we can just go ahead and use a table to do it. If we can just build a table from the bottom up, okay? So the motivating example here that we're going to walk through this process through is computing binomials, because doing Fibonacci, that's too easy, right? So consider the following, right? N choose k. That's the number of ways of choosing k elements as a subset of size k from n elements. So for example, 10 choose 5, right? How many ways are there of choosing 5 things from a set of 10? So if I had 10 students, say, out in the hall, I needed to choose 5 of them for an experiment or something. So how many ways are there of doing that? 252, okay? Now over here, we've got this classical combinatorial definition of this, right? Combinatorial definition being n factorial divided by n minus k factorial times k factorial, okay? So let's go ahead and do that over here. Does anybody know how to do factorials in Python? R is equal to n. Can I do this? Certainly I should not be able to do this probably, right?
Python's pretty smart.
It's the not operator, right? So let's go ahead and bring in the math library, import math, right? And I think that there's a math.factorial. There we go. That'll work. Now just make sure that your denominator is mathematically correct, right? I can't believe how many times on like Reddit I see that PEMDAS issue come up again and again, and people continue saying that it's like, I forget what the answer is, but no, it's this way. No. I think at this point those people are just trolling, trying to get other people convinced about bad math, right? Let's go ahead and print this out in a formatted manner so that n choose k is equal to whatever the result is, okay? Go into these 310, there we go, Python, binomial. Now, if we're correct here, then we should get 252 just like Wolfram Alpha did. Oops, what's wrong? Oop, I just didn't, nope, closing, there we go. So 252. Note, however, though, it's going 252.0, right? And that's because factorial is operating on floating point numbers. So let's kick it up a notch and see if it still works. So up front here, we're doing a Python thing because I spent at least 10 minutes to get this to work. And so you'll suffer with me for 2 minutes to see how I got it to work, right? So 100 choose 50, right? Is that right? Well, let's find out. 100, choose 50. Because, of course, Python has multi-precision built in, right? You can have an arbitrarily large integer, right? Right? So it begins with 100 and ends in 256. I'm not going to verify everything else. Okay, well, how do I get all those last digits since it's in scientific notation? We'll force it to print all the digits. There we go. Are all the digits correct? 264. No. We lost some precision there. So, does Python really have multi-precision floating point numbers? The answer is no, not by default. Right? By default, there are only 28. This is just a Python thing here. 28. There are 28 digits by default, digits of precision by default. Floats are not multi-precision numbers like integers are in Python. Did anybody know this? I didn't know this until I tried, preparing for this and going, okay, well, we'll just do a. I asked the question: is there a factorial built in? Yes, there is. Okay, it worked for small numbers, doesn't work for big numbers. Right. So let's find out what happens. What you can do is you can set the precision. Right. So I'm going to go ahead and import another library over here, decimal. Import everything. And what I'm going to do is I'm going to reset the precision. Get context dot precision, and I'm going to set it to 100 digits of precision. Okay. And then will that work? Still no. Why? Because these are still floats. What you have to do is you have to treat them as decimals. Right? And at this point, it begs the question of, well, if you have to go to such lengths to get this to work, can you really say that it has multi-precision built in? Not really. This is more like working with big decimal or big integer in Java, right? Say what? Nope. There. Now we get the right answer. All right. It's printing out 100 decimals of digits of precision. So floats are not decimals. Right? Floats are going to be primitive types built into the language. Decimals are other types built into a library that's standard in the language. Yeah.
Isn't multi-precision one of the things that Pythoners brag about?
Well, I mean, yeah, they're right for integers. You can have arbitrarily large integers. That's perfectly fine, right? But if you want to do like multiplication by an integer, that's fine too. Division, that's no longer an integer, is it? Right? Now, technically, it should be an integer because this n factorial over n minus k factorial, that's always guaranteed to be a whole number, right? But in these, it's the fact that for whatever reason they decided to deal with floats in the math library for factorial. It doesn't make any sense to me. Right? It should only be integers.
You can't factorial like 3.5 or something.
Right, exactly. Now, what you could do is you could roll your own, right? You could say 100 times 99, 99 times whatever, right? You could write your own loop to do this, and then divide the bottom part, et cetera, et cetera. So you could get around that without using the math library, but I just found it interesting that this is how you actually have to do it if you want to use floating point numbers with arbitrary precision. Right? So we did get the final answer here correct. Okay. All right. I want to work it another way. Right? Another way is to use Pascal's identity. So this is where recursion comes in. Right? So Pascal's identity is that n choose k is equal to n minus 1 choose k minus 1 plus n minus 1 choose k. Okay? That's Pascal's identity, and you might have seen it before, hopefully. You also have some base cases here, right? Base cases, right? Where if you have n choose n, in other words, k is equal to n, or n choose 0, then that's 1. Right? Why? Because if you have 10 things, how many ways are there of choosing all 10 of them? You take them all, and that's it. If you have 10 things, how many ways are there of choosing none of them? You choose none of them, and that's it. Right? This is the number of sets, and this is the number of empty sets. How many empty sets are there? There's just one, the empty set. Okay. So what I want to do is I want to implement this in a recursive manner. Okay. This is the step one, right? In fact, we'll reveal this to be the FAST method, F-A-S-T method. We'll define that later here. But I want to go ahead and have def binomial, right? N-K, right? So this is going to returns the value n choose k. Okay. There's the documentation. All right. So what I need is a base case, right? This is the recursion. If n is equal to k, or if k is equal to 0, those are my base cases over here, right? And I'm going to end up returning 1. Except that I can't use pipe. What do I use in Python? Or, right, yep. Yep, the keyword or an and instead of ampersand, pipe, right? Else, I'll return a recursive call to this. Return binomial of n minus 1, k minus 1, and add binomial of n minus 1, k. That's Pascal's identity right there. Okay? All right, let's go ahead and call that. Result is equal to binomial. Now this is all going to be pure integers, so I'm going to erase that f so that it doesn't format it as a floating point number. But now I'll go ahead and go with, let's kick this down to 10 and 5 and k. Okay. Now again, 10 choose 5 is 252. It works. Okay. Let's go up to 150. Remember that it's going to be something like this. Right? Begins with 100, ends with 256. Right? While we're waiting for that, let's come over here and understand what's going on. Right? Now, normally I would visualize, say, Fibonacci, right? But this is binomial. So if I go binomial of n choose k, right? Then I'm making two calls, n minus 1, k minus 1, and n minus, actually let's go ahead and do actual values here, 10 and 5. I make two calls, 9 and 4, and over here, 9 and 5. I make two calls, 8 and 3, and 8 and 3. No, sorry, 8 and 4. 4. There we go. 8 and 4, and 9 and, or 8 and 4. Right, there we go. 5, sorry. Right. Two calls there. 7, 3, 7, 5. There we go. Or, yeah, what? Go ahead.
On the left one, you decrease the left number.
Yeah, you decrease both by 1.
Okay.
You decrease the first one by 1 because that's what Pascal's identity is.
Okay.
N choose k is equal to n minus 1 choose k minus 1 plus n minus 1 choose k.
Okay.
Right? So 8, 4, 8, 5. This one goes to 7, 3, and 8, 7, 4. Right? That's 7, 4, and 7, 5, right? Dot, dot, dot. These will go to, dot, 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 right? So the idea here is that you have a lot of repeated computation. Now, I'm not going to go too far and too deep into this, but you see 8 and 4 were computed at least twice, right? 7 and 4 were computed at least twice. When you get down to it, 2 and 1, that's going to be computed an exponential number of times. Right? So let's go ahead and kill this because I suspect that this will not run within our lifetime. Why? Because there are going to be that many function calls right there. Right? And even if you do, say, 1 trillion function calls per second, right, which is a tall order for whatever AWS this is running on or whatever it's running on, right? That means that that's that many seconds. 2 years. 3.2 trillion years, at least according to that estimate. All right. Okay. Let's kill it with fire. Right. There we go. In fact, let's go back and understand that just to even compute 10, choose 5, how many function calls are there? Total plus plus. Oops, can't do that. Plus equals 1. So let's go ahead and go with total equals 0 and print the total function calls. Total function calls. There we go. Oops. What do I have to do a global variable in Python? Is it like this? There we go. I just have to put it in the scope, and then I can work with it. All right, there we go. 503 function calls. So we're facing twice that many function calls. So it's not even 3.2 trillion years. In fact, let's make our processor 1,000 times faster, right? Even if I give the benefit of the doubt of the processor, it's 3.2 billion years, right? And that's an overestimate on the power that we're running on this processor, right? That is not at all acceptable, right? So what dynamic programming does is it steps in and says, well, wait a second. What if you use memoization, okay? So let's go ahead and write something with memoization. So what is memoization? Memoization is when you compute that one value the first time, 8,4, go ahead and pay for the recursion, right? You will have to pay for the recursion, but you only have to pay for it once. And anytime you see it again, a second time, you don't pay for the whole recursion again. Instead, you cut out that branch of the computation and you reuse it because you remember it. You cached it in a table. Right? So help me write that. Right? I'm going to bring in a map to do it. Okay? That map computes the value n choose k using memoization. The given map is assumed to be a dictionary mapping nk as a tuple to the value n choose k. All right? Okay, there we go. Oops. There we go. All right, so what we do is we check the map. If n choose k is in the map already, right, then we simply use it. Return map.get n choose k. nk. There we go. If it's not in the map already, then that means that we need to pay for the recursion. Now, first of all, what we'll do is we'll take care of the other base case here. Elif. There we go. If n is equal to k or k is equal to 1, then we'll return 1. Okay? Otherwise, we'll pay for the recursion. Right? That we'll go ahead and call binomial memoization on map n minus 1, k minus 1. And then again on the same map, n minus 1, k. That's Pascal's identity. Pascal's identity right here. Right? This one. Right? But we're using a map as well. And the first thing we do is we check that map. Now, I computed a and b here because I want the result. A plus b. That's Pascal's identity right there, adding those two things together. And then I'm going to put it in the map. Map of n, k is equal to r. And then return r. So again, the first time that we see it, we pay for the recursion. But every time after that, it's going to be in the map, and we don't have to worry about it anymore. Okay? Let's see. Do I have to set up the map? I don't think so. So binomial memoization, I'll just go ahead and go with an empty dictionary here. Map, dictionary, I'm using those terms interchangeably. Okay? Now let's go ahead and make sure that it works on a small number, 10 choose 5. Right? Oops. Oh, I got rid of the total, so let me go ahead and get rid of that. There we go. 252. All right. Let's pump that back up to 150. And let's see if we get an accurate result now, right, without 3.2 trillion years of wait time. Right? Hey, it was instantaneous. And it was 100,891, blah, 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 blah. And it ends in 256. I'm convinced that it's the same. Okay? So, That's memoization. That's something I cover in Computer Science 1 even. Right? But now what dynamic programming does is it steps in and says, do you even need this recursion at all? Okay? And by that, what we mean is, well, think about what you're doing here, right? You are computing n choose k, but you're doing it using Pascal's triangle. So you go n minus 1, k minus 1, n minus 1, k. And then that again, it goes into n minus 2, k minus 2, n minus 1, 2, k minus 1, 2, sorry. So it keeps the same. I keep confusing these, sorry. 1, dot, 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 dot. Right? So think about all the values of k. K can run from 0 or up to k itself, right? So that's a bad way of writing that. Think about, let's rewrite this. Think about this as I choose j, right? What values does I run from? Well, it runs from n down to 0, or equivalently, if you want to look at it from 0 up to n, that's fine too. And then j runs from k down to 0, or again, equivalently 0 up to k. So if you were to write this as a table, it might look something like the following. Come on. Come on. Dynamic programming is right here. There we go. And as you can tell from that file name that I just gave you, what are we doing here? Pascal's triangle. All right? It's just that it's written as a table instead. Right? We've got Pascal's triangle here from the top to the bottom, and each one of these rows is a binomial coefficient. 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, dot, dot, dot. We call this Pascal's triangle because of Pascal's identity. N choose k is dependent on the two previous values right above it. For example, 6 is going to be the one above it plus the one above it, and to the left of it, 3 plus 3. You take 3 plus 3 and you get 6. You take 3 plus 1 and you get 4. Right? Now, on the outskirts here, those are our base cases. Why? Because 4, choose 4, is just going to be 1. 4, choose 0 is going to be 1. Right? So all along the diagonal and along that first column are all going to be 1s. Usually, again, it's written like this, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. It's written like a triangle like this, an equilateral triangle. But I want to emphasize that this is a table, right? Or if you want to get fancy about it, remember dynamic programming was just a fancy marketing term. If you want to get fancy about that, it's a tableau. And people use that term all the time. Right?
Is that how they say it?
Yeah, tableau. Because French, I don't know. All right, so this is a fancy tableau. So in other words, we can eliminate the recursion entirely, right? All we have to do is fill out this table in a couple of for loops. Right? What would that look like? Well, if each entry is dependent on the one right above it and the one right above it and to the left, in what order should we fill this out in? Top to bottom and left to right. If we do that, and we do it like this, right, then that ensures that whatever entry we need will have the previous entries already computed. Now, of course, you might want to go through and set it up so that you are setting these base cases, 1, 1, or you'll have, an extremal case where you just have to ask yourself, is this, am I in one of those cases? If not, then go ahead and look at the previous values over here. Okay? So let's do that. So, def, binomial, dynamic programming. Right? We're not going to take a table. We're not going to take a data structure or anything. We're just going to take n and k, right? Produces the value of n choose k using dynamic programming, right? By filling out a tableau of Pascal's triangle, right? All right. So what would that look like? Now, I don't want to deal with, Python is not that great at two-dimensional arrays, two-dimensional lists, because you'd have to go through and you'd have to initialize everything. So I'm going to use the same solution as before, a map, but I'm going to do it locally. I'm not going to do any recursion whatsoever, okay? This is just my little trick here to avoid having to have a list of lists, right? And what I'm going to be doing is I'm going to be mapping I, j pairs to I choose j values, okay? The tuples, right? So there's my tableau C, C for choose, right? For I in range from 0 up to n plus 1 minus 1, that gives me all the way up to n. Why? What were the values of I and j? Goes up from 0 up to n and from 0 up to k inclusive. And that's why I want to go plus 1 there. Okay? I will go for j in range of 0 up to, let's see, what would it be? It's minimum of I. We'll talk about that, why it's like this in a second, plus 1. All right? So if a base case, in other words, if j is equal, or let's model the same base cases that we've got up here. If I is equal to j, right? Or, did I use it? Yeah, j is equal to 0. Then C sub I j will end up being 1. Else C sub I j is equal to, and here's where Pascal's identity comes in. It's going to be C sub I minus 1, j minus 1, C sub I minus 1, j. So let me copy this, plus this, and subtract 1 on both of these, and subtract 1 on the first one of the second one. Okay? Yeah, go ahead.
So technically, can we use the 2D array?
You can, but like I said, you'd have to initialize it with a list of lists. So you'd have to go, an alternative would be C is equal to a list, right? And then for I in range of 0 up to n plus 1, you'd have to say that C sub I is equal to list. And then you'd have to append, et cetera, right? Or 0 for I in range of 0 to k plus 1, right? I don't want to do that. That's ugly. Why use lists when you've got maps? Or why use lists when you've got dictionaries, right? There's no going back once you've seen a smart data structure. All right, let's go ahead and print this out to see if it working. Let me kick this back down though to 10. Actually, let me kick it down even further. I don't know, 6 choose 3. There we go. Oh, come on. I'm not calling it that, that's why. Binomial dynamic programming and N and K. There we go. All right. So do you see all those values there? For example, 6 choose 3, that's going to be 20. That's the one that we're interested in. Right? But otherwise, you can kind of see Pascal's triangle here. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Right? Do you see the patterns here? 1, 3, 1. There's the second row. Right, their third row, excuse me, a fourth row actually because it starts at 0. And then here's the next row, 1, 4, 6, 4, 1. It's symmetric, right? And 1, 5, 10, 10, 1. Yeah. Then it's no longer a triangle, is it? Right? Why is it no longer a triangle? It's a triangle until you hit this, and then it becomes a kind of a polynomial or polygon, right? What would that be called?
It's a trapezoid.
Well, it's kind of like a trapezoid, but it's got 1, 2, 3, 4 sides. But It's not a regular trapezoid, at least. I don't know what it's called. It's a polygon. So it's not really a triangle because you're not filling out the whole thing. You're filling out the triangle, but then it's skewed like this, right? So we don't need to print it. We just need to return the value that we're interested in. Return C sub n k. There we go. And 6 choose 3 is what? 20? Let's ask and make sure. 6 choose 3 is indeed 20. Remember that 10 choose 5 was 252. So let's make sure that that works as well. 252. And 100 choose 50 began with a 100 and ends with a 256. I'm convinced that it's correct. Right? But look at the beauty of that. Right? Did we have to do any recursion at all? No. So what we just went through was called the FAST method. Let me pull that up here. In fact, it's over here. All right, there we go. So with all the dynamic programming solutions that you're going to see, they're pretty much all the same because they go through this FAST method. The FAST method is that you design a first solution. Right? That's going to be your recursion, right? You come up with a recursive way of looking at it. You analyze that first recursion to see where are the redundancies, right? If you were to write that out in a big giant computation tree, you see that you're computing the same thing over and over and over again. You identify the subproblems and say that, well, I only need to compute that one and that one and that one, and I can that one and that one combine to form a solution for this one up here. Then you turn their solution around. Instead of using recursion, you identify the table that you have to fill out, the order in which to fill it out in order to have all the solutions, and you're done. Right? Then it's just a bunch of simple for loops. Okay? So that's what we did here. We started out with our first solution being the bad recursive solution. We identified all of those, all of the redundancies by saying, well, okay, well, I don't have to compute n minus 1, k minus 1 over and over and over again. Just put it into a map and reuse it. Right? And then we identified, well, we don't have to do that at all. We don't have to reuse recursion at all because if you look at it as a table, right, Pascal's triangle, then you just have to fill out the table. Right? Screw the recursion entirely. Right? You don't have to do it. Right? And so that's what we're going to look at with respect to some other problems here. Right? Again, the basic steps as far as my notes would be concerned would be, I don't know who deserves credit for this FAST method. I think it was a blog post many years ago. That blog post, or it's been identified and reblogged a million times. So does this even have an author? So 2017, Byte by Byte. I don't know if this appears in any like actual books or anything. I don't see an authorship here at all. So in academia, if we don't know who came up with the first one, we call it a folklore solution, right? Well, somebody did it. Nobody knows who, but so it's folklore. So, you know, but nobody ever wrote it down. So the first person to write it down and says, "Well, I can't take credit for it, but it's a folklore solution. But here it is." And then they get cited because they're the first ones to actually write it down and publish it. Unfortunately, I don't see any. There's an ebook, I guess. Whoever wrote this ebook or whatever, right? Question online. I have no idea what this question is asking, but just random internet folks. If you do have a question, go ahead and put it online and or rephrase that if you want. Anyway, I'll go ahead and put this in the notes so that you have it at least. Python. All right, if you want it, that is. But again, the basic steps are that you identify the value that represents a desired solution, optimal solution to a problem. In this case, it was n choose k for an n and a k, right? You identify a recurrence identity in terms of smaller values of the problem. These are called sub-solutions, right? You use math to do this, to prove your recurrence is correct, right? This is often referred to as the optimal substructure property. And it's just simply an application of induction. You would prove that it's true for the base case. You would prove that it's true for this case, implies that it's true for the other cases. In other words, if you were Pascal 250 years ago or something, you would end up coming up with an inductive proof of this thing, right? And you can come up with an inductive proof of, if you like, as well now, right? With using 235 material, right? Professor Honor Motlow just had a on this morning. Thanks. Okay, I don't know if it's intended for me or not, but anyway, okay. You identify. Oh, sorry. All right, identify the trivial base cases. You identify the final desired result. Because, of course, that's just recursion, right? You identify the base cases. That's the first thing you do in a recursive function. You identify the desired final result. That's your entry point into the recursion. And then, of course, you use math to prove that, well, here's the recurrence that works, right? And that's your recursive calls. Then you design a table, or, again, tableau, that holds values for each subproblem. Right? Possibly, you may need to keep track of additional information, right? In order to build the actual solution. Why? The table may only hold the optimal values, not the values that gave you those optimal values. So you may need to keep track of an additional table or so. You then design your loops to fill out the tableau, in an order such that the needed subproblem solutions are available. Right? Because if we went back to this, if we tried to do it from the bottom up in Pascal's triangle here, right? If I started at the bottom and worked my way up, I wouldn't have the necessary solutions to compute this solution first. So all you have to do is come up with, okay, well, this solution depends on that solution, and this solution depends on that solution. So that means that I need both of these solutions before I have this solution. So if I fill it out top to bottom, left to right, I'll have all the solutions that I need. Okay? All right. Then you fill out your table, and that's it. All right. We're going to look at two more examples here that you're going to be programming, not for this week, but for next week. One of them is going to be examples. Optimal binary search trees, and the 0-1 knapsack problem, which you've already seen, but we'll review. Remember that you're a thief and you're trying to steal the most valuable things, but you can only carry so much. So you want to optimize the value of the things that you steal, subject to your weight constraint that you can't carry more than that. Right? Optimal binary search trees, though, in the last 10 minutes here, let's motivate those. Okay. So let's say that I've got, I don't know. You know what? Let's pull out an actual example here from like an old quiz or something. Assignments. I haven't given a quiz in this course in a long time, but I never give quizzes in the H course, only in the summer course. No, I don't want this. Not assignments, but do I not have any quizzes? Oh, I haven't given quizzes since COVID, apparently. No. Darn it. Maybe in the final? Bear with me here. Hopefully this example will be worth it. It's compiling. No. Oh, yep, here it is. Okay. All right, so some sports are more popular than others, right? Hopefully we can agree on that. There's baseball, there's football, there's hockey, there's shinty, and there's shirling. One of those is fake, by the way. All right, guess which one? All right, there are two of them you haven't heard of. All right, shinty and shirling. All right, shinty is real. Shinty is Gaelic field hockey. All right. Look it up. It's a comedy skit. Shinty. Yeah, there it is. Shinty goals from the 2013 season. It's. Come on, let's get to actual gameplay here. So it's kind of it's field hockey here, kind of.
They hit a ball.
Yeah, they hit a ball. It's kind of like field hockey, right? But it's real. It's real. You find now. I would add to this kabaddi. Anybody heard of kabaddi? So I never heard of it until it's basically tag. Is it kabaddi? Kabaddi. No, that's not how you spell it. Kabaddi. Yes, there it is. Kabaddi is a contact team sport. It's basically Indian tag, right? I think. That's how I would describe it, at least. But I only found out about it once I just subscribed to Hulu, and then I got all these suggestions just because I liked hockey one time. Hey, you might like kabaddi. Anyway, the idea here is that some sports are more popular than others, right? So what if I were to build a binary search tree based on these search terms, right? And meaning that we are going to look at this from the perspective of alphabetic order, right? So, for example, shinty. If I put shinty up here as the root, then that means that B, F, and H all have to go to the left subtree because alphabetically they're less than shinty. Right? Shirling has to go over here to the right, and so football, F, B has to come before that, H has to come before that. So it follows the binary search tree properties, right? But is it optimal, right? What's the expected number of key comparisons in this tree? Right? So to get to shinty, if you're searching for shinty, how many comparisons do you have to do? Just one, because you start at the root, right? Comps. I'll bring it over here in a second. One. Right? So number of comparisons is one. What was the probability that somebody would actually search for shinty? Right? 4% apparently. Okay, so 0.04. What about the others? What about baseball, hockey, football? Sorry, I don't like basketball very much, so that's why I didn't put it in there. And shirling. And that was just a joke, right? So what about football? To search for football, how many comparisons would you have to make to find it? One, to realize that I need to search in the left subtree. Two, to find it as the root of the left subtree. And it has a probability of 35% here. So 0.35 and 2 comparisons. Hockey, that would take 1, 2, 3 comparisons to find. Just like baseball. Oh, sorry. Football would be 0.35, right? And baseball would then be 3 comparisons. Hockey, 3 comparisons. And shirling, 1 comparison. I'm just copying these down really quick. 0.40. Hockey is going to be searched for 13% of the time. And shirling is going to be 8% of the time. There we go. So what are the average number of key comparisons needed to search on average any one of these terms? All right. What you do is you multiply these things together. 2? Was it 2%? I thought it was 8%. Oh, sorry. 2 comparisons. You're right. 2. So 0.04, 1.20, 0.39. This is 1.05 and 0.16. Add those all up, and that was the answer to the quiz that I gave. What was it? Was it 70? Oh, because 2. You're right. 0.70. Right. What's that going to be? 9. Carry the 1. 3, 6, 7, 4, carry the 1, and 2.49. Right? Do I have... I don't have solutions turned on here. Right? So 2.49. Right? Is that optimal? Could I do better? I mean, baseball is way down deep in the tree, requiring 3 comparisons, even though it is the most common search term according to this known distribution. Is there a better way of doing this? This is kind of a balanced tree, right? There are 3 keys on the left side. There's 1 key on the right side. If I were to rebalance it to the right, doing an LR or R rotation, like in an AVL tree, right, I would just get a little bit unbalanced to the left or to the right instead of the left. So it wouldn't really change anything from the balance perspective. But would it change something if I put baseball at the top in an unbalanced tree? Let's try it. All right, so baseball at the top. All right. Yeah, there we go. All right, now, everything is greater than baseball. So football, hockey, shinty, shirling. Let's just go ahead and put hockey over here. All right, actually, yeah, hockey, and then football, and then we can go with shinty, shirling, shinty, and then shirling. I'm thinking of, I have to think really hard for alphabetic order. This is correct, right? All right. So how does this change? The number of comparisons for baseball then becomes 1. And we still search for it 40% of the time. Hockey becomes 2. Football becomes 3. Shinty becomes 3. And shirling becomes 4. Right, what were the key distributions before? Shinty is 0.04. Right, shirling is 0.08. Football was what? 35, and then 13. 35. Right. Now, is that better? Should be, probably, right? 32, 0.32, 0.142, 105. I don't think it's going to be better. Maybe not. 0.40, 0.26. Oops. What's that going to be? 4, 5, carry the 1. 5, 6, 7, 8. 1, carry the 1. Yeah, it is better. 2.158 comparisons. The other one was 2.49. So, it's even better. Is that optimal? Is that the best you can do? Yeah. What if we make it even deeper and put football up here, forcing hockey to come down here, shinty and shirling then go down even further? In other words, we end up making this into a linked list instead of a tree, right?
Would it be better if you had like football and hockey both B2 and then
Maybe, right? I don't know what the optimal solution is here, right? That is where we use dynamic programming to compute the optimal binary search tree, okay? Now, the optimal binary search tree, we'll talk about this next time, but basically, you have a choice. If you've got keys K1, K2, ... Kn, which one should be your root, right? Suppose that you choose KL, right? And that means that all the keys over here in the left subtree end up being K1 through KL minus 1, and all the keys over here in the right subtree end up being KL plus 1 through Kn. Right? Now, if that for L running from 1 up to N, right? Those are all your possibilities. Now, here's the recursion. Suppose that you found the best one. Well, now what should be your root for your left subtree? What should be your root for the right subtree among these keys right here? Right? This is the first step in the FAST sequence, right? Your first solution. You come all the way down and you realize that, well, what if I only had one key? What's the optimal tree? right there, the seed, right? Meaning that you have one comparison times the probability of searching for the key K. Right? Now what we need to do is we need to come up with a bottom-up solution that defines a recursion, and then we'll come up with a table, we'll come up with a way to fill out that table, and then we'll come up with the final solution. By the way, if you prefer, I do have a pre-prepared video series on this optimal binary search tree using the light table, right? So if you go to Canvas, right, we're already too late here, so I'm not locked in, but there's a link to it in the Canvas. The light table is the one where it's I write backwards, right? It was pre-prepared a couple of years ago if you want to check that out. But it's going to be a lot more detailed than what I'll do on Wednesday. All right. See you then. Remember, your assignment 8 is due on Wednesday.